Hello, this is Jerry Pinter, and welcome to our lecture on Chapter 8. In this first part of the lecture, we will be looking at static equilibrium, stability, and balance. Chapter 8 is broken up into two parts. In this first part, we'll look at the static equilibrium of extended objects and also stability and balance. And in part 2 of this lecture, we'll look at springs and Hooke's law and also elasticity, stretching, and compression. So what do we mean by static equilibrium of extended objects? Well, we learned earlier in the course that static equilibrium basically means an object that is at rest. Now, it was simpler with what we did before. In Chapter 5, we considered static equilibrium of simple objects that were modeled as a particle or point mass. And our only condition for static equilibrium was that the net force is equal to zero. Now, for extended objects, what we're doing in this section, the condition net force equals zero is not enough for static equilibrium since the object can rotate. So to see what this means, take a look at this demo example down here. So we've got an extended object. Think of this like a box, let's say sitting on a table or something. Now, if we push with two equal and opposite forces on each side of the box like this, obviously the box is not going to move. These forces are balanced and there's no net force. And also because these forces are pointing towards the CG or center of gravity of the box is not going to rotate either. But now take a look at this example here. We've got the same box, the same two forces. So again, the forces balance each other and the net force is zero. However, now each of these forces is going to cause or create a torque, which is going to cause the object to rotate. So let's take a look at this. Here it goes. So you can see the forces are causing a twisting motion on the box. It's causing the box to rotate in a counterclockwise direction like that. So this object is definitely not in equilibrium. Okay, it has no net force, but it does have a net torque that causes rotation. So in other words, we need more now to have static equilibrium of an object. We need not only the forces have to be balanced and so that there's no net force, but we also have to make sure that the torques are balanced so that there's no net torque. So our requirement for static equilibrium now for an extended object is the following conditions. No net force means all the force components in the x direction have to add to zero, all the force components in the y direction have to add to zero, and if it's a three-dimensional problem, all the force components in the z direction have to add to zero. And in addition, we require that there is no net torque on the object. In other words, when we add up all the torques, we need to make sure that those are also equal to zero. Now, when we figure out net torque, we have to choose a pivot point usually. And it turns out that any choice of pivot will work, but some choices are definitely better than others. We'll see as we work through some examples how we select the pivot point. In general, it's usually a good idea to choose the pivot where an unknown force acts, and you'll see this in some of the problems that we work on. So let's take a look at some examples of static equilibrium and extended objects. So this first one is a pretty basic example. We've got the playground seesaw or teeter-totter, and we've got the two kids sitting on it, and you can see there's a balance fulcrum point right here. So we have Ryan and Tyler want to balance on the seesaw. Ryan's mass is 40 kilograms. That's the big kid here. And he sits 2 meters from the pivot. Where should Tyler sit? So they want to balance the seesaw. They want to be balanced like this so that it's not rotating. And we're told that Tyler's mass is 20 kilograms. So we're trying to figure out this distance right here. And also we're going to ignore the weight of the seesaw in this problem. So our condition for static equilibrium here is just for no rotation, we want to make sure that the sum of the torques is 0. All right, so we've got, let's go ahead and add up our torques here. So this is Ryan on the left, and his force is pointing down, of course. His weight is mg, which you can calculate to be 392 by taking his mass of 40 and multiplying it by 9.8. And Ryan is trying to rotate the seesaw in a counterclockwise direction, so his torque is positive. So I've got 2 times 392, that's Ryan's torque. And then for Tyler over here, his torque, remember his weight, of course, goes down, and mg here is 196 based on his mass of 20. This torque is a negative torque because Tyler is trying to make this thing rotate in this direction, in the clockwise direction, which is negative. So we're going to subtract his torque. And we don't know this distance, that's what we're going to calculate. So his distance is d times his weight of 196, and of course we have to add those together to get 0. So multiplying these two numbers, we get 784, and let's move this term, it's minus, let's move it over to the right side, it becomes positive, 196d, therefore d is 784 divided by 196, which is 4 meters. Now let's take a look at this answer and see if it makes sense. You might have been able to do this problem in your head. Notice that the big kid here, 40 kilograms, is exactly twice the mass of the smaller child, 20 kilograms. If his distance is 2 meters over here, then we know the smaller child must have twice the distance in order to get the same torque with only half of the mass and weight. So therefore, that's why twice of 2, 2 times 2 gives us the distance of 4 meters. So here's another fairly basic example. A woman of height 1.7 meters lies on a light board supported by 2 scales at her feet and head as shown. All right, so here she's lying on this board. Each end of the board is supported by a scale, and notice this scale reads 315 newtons and this scale reads 350 newtons. The distance, again, between the centers of the scale there is 1.7 meters. That is her height. And we're going to ignore the light board's weight in this problem. We'll assume that it's really lightweight. So the first question, part A, what is the woman's weight? Well, in this part of the problem, all we need to do is, we notice that she's in equilibrium. She's not static equilibrium. She's not moving at all. So the sum of the forces in the y direction must add up to 0. So this part, is pretty straightforward. The upward forces on her are these 2 scale forces or readings. So we have 315 newtons pointing up at her feet. We have 350 newtons pointing upwards at her head. And we have her weight pointing down, which is unknown. So we can say 315 up plus 350 up minus her weight is equal to 0. So therefore, her weight is equal to the sum of 315 and 350, which is 665 newtons. Okay, so all we're doing here is just balancing the forces in the vertical direction. Now, this should be part B here. Where is her CG relative to her feet? So here we're going to have to balance the torques. Now, it's not super obvious when we look at this problem where the pivot is. All right, this is not like the seesaw problem. So we have a choice. We can choose a pivot wherever we want. So what we're going to do here is just pick the pivot at one of these 2 ends here. So let's choose the pivot to be at her feet here. All right, so this black dot represents where we're going to consider her rotating about. Now, of course, she's not rotating, but what we have to do is make sure that all the torques add up to 0, and we're taking the torques with reference to this point right here. All right, so down here we can make a little coordinate axis. This is our origin at the pivot, 0. This is her CG. Remember, all of her weight, which is 665 newtons, acts downward at her CG. All right, we don't know where this is. Let's just call it X, and we're going to solve for X. We do know that up here, there's a 350 Newton force pointing upward. That's the scale right here. And it is at 1.7 meters, which is her height. So let's calculate the sum of the torques, again, using this as our pivot. So we've got, in the positive direction, this force here tends to rotate her in a counterclockwise direction. That's our positive direction. So we have 350 newtons times that distance, 1.7 meters, right? We're measuring the distance from the pivot now. So we have 1.7 meters. And then this force here, her weight, remember, acts at her CG. So we have 665 newtons times the distance x, which we're trying to calculate. And remember, of course, this is a negative torque. Her weight is trying to rotate her around the pivot in this direction. So now you might be wondering, well, what about this force? Don't we have to calculate the torque here? Well, we don't, because this force acts right at the pivot. So the distance from the pivot is 0. So this torque is basically 315 times 0, which is, of course, 0. So we never have to include forces at the pivot. Only these two forces here have to be included. So we have, let's see, this, I'm going to take this 665x and move it over to the right side, and then flip the equation. So I have 665x equals this product here, which is 595. So therefore, x is equal to 595 divided by 665, and that is 0.89 meters. That's the distance here from her feet to her CG. A classic problem in the study of static equilibrium of extended objects is the so-called scaffolding problem. And the last problem we just did with the woman lying on the board is technically a scaffolding problem as well. This is what they normally look like, though. You have two painters standing on a board here, and there's cables that raise this board up and down the building so that they can paint. Their weights are shown, so this guy has a weight of 200 newtons, this guy has a weight of 150 newtons, and we're told that the scaffolding itself weighs 100 newtons. All right, now remember the weight of the scaffolding, we put it at the CG, okay? And of course, the CG of the scaffolding is halfway across, so it's going to be somewhere around here. Furthermore, it says if the tension in the left cable is 300 newtons, so that's this cable here, 300 newtons, find the tension in the right cable. So we're trying to find out what T is here, all right? So in this problem, there's only one unknown force, and that is this tension right here. We don't even have to balance torques. So this problem is significantly simpler than most scaffolding problems, but it's a good one to start with. All we have to do here again is just balance the forces. So we are in equilibrium. So the sum of all the forces in the y direction is 0. So let's just add them up. In the positive direction, let's call that up. It's 300 newtons here plus T, all right? And then all of these forces are pointing down, so we're going to subtract them. Minus 200, minus 100, minus 150, and all of that has to be equal to 0 because we're in static equilibrium. So this T here, basically if you take these four numbers and add them all together, we get T minus 150 equals 0. Therefore, the tension in this cable is 150 newtons. Here's another example, which is very similar to the scaffolding problem. So here we have a woman standing on a 2-meter long board, and on each end here, the board is sitting on a scale, all right? And we want to know what is the reading on each scale. So she is standing 1.5 meters from this end, as shown, and her weight in newtons is 650 newtons. What else do we know? The board has a weight of 300 newtons, okay? So let's go ahead and how do we do this? Well, again, this is an example of static equilibrium. So we have to make sure the torques and the forces all go to zero when we add them up. So we have to pick a pivot again. So let's choose our pivot at one of the scales. So let's just pick A over here. All right, so the sum of the torques about this pivot have to be equal to zero. So let's take a look at the forces involved here. We've got the board here. So remember the weight of the board was given as 300 newtons. It acts right at the center of the board because that's where the CG is, all right? That one's, for a uniform board like this, the CG is always in the middle. The woman is standing over here and her downward force of gravity is 650 newtons. That's her weight. What we don't know is we don't know what FB is, that's the force on scale B, and we don't know what FA is, the force on scale A. But for doing torques around this point here, the FB is a positive direction torque because of the counterclockwise direction. So we have FB times 2, all right? Where's the 2 come from? Well, that's the length of the whole board here, right? That's how far away this force is from our pivot over here. Minus her weight times 1.5 is the distance, all right? And it's minus, of course, because this is a negative torque in the clockwise direction. And then the board here, if the board is 2 meters long, we know the CG is 1 meter from the pivot. So we have 300 newtons of weight for the board times 1 meter is the distance. And all of that has to equal to 0. So basically, we can multiply these two numbers and add it to this number, add everything together, and solve finally for FB, the force on scale B, and that ends up being 1,275 divided by 2. All right, we're just doing some algebra here to solve for F sub B. And our answer then is 637 newtons. So that's what this scale will read, okay, 637. Now, we still have to figure out what this scale reads, all right? Well, we know that the forces in the y direction all have to add to 0, and we know what all the forces are now, except for FA, and that's the one we're going to solve for. So we know that FA plus FB, those both go up, those are pointing up, equals negative 300 pointing down, minus 650 pointing down. That's why we have the minus signs in there. All right, so we can solve this for FA. FA equals, we add these together and bring them to the other side. We get 950 minus FB when we move it to the other side. And remember, FB is 637. So our answer is 950 minus 637, which is 313 newtons. So that 313 is the reading on scale A, and scale B, remember, had a reading of 637. So here's another scaffolding problem. This one a little more difficult than the previous one. We have 2 workers of mass 100 kilogram here and 70 kilograms here are positioned on a 50 kilogram scaffolding as shown. So the scaffolding, the board here, also has mass equal to 50 kilograms. And notice all the dimensions are shown here. This tension 1 of this cable is 1 meter from the end. Tension 2 in the second cable is 1 meter from this end. And also this guy is 1 meter from this cable. The smaller guy is 2 meters from this cable. All right. And our goal here is to find the tensions T1 and T2 in each row. So what I've done here is sort of drawn our free body diagram for the scaffolding. We got the 2 tensions in the ropes going up. We've got the 2 weights of the workers going down. And then I also drew the weight of the scaffolding, which remember mg, that would be 50 times 9.8, is 490 newtons. And of course, that acts at the CG of the scaffolding, which is halfway across. So these are all the forces involved here. Now, we can choose a pivot anywhere we want. It's usually a good idea to pick the pivot at one of the unknown forces, because when we do torques, remember, we don't have to include this force now, T1. We don't know what it is anyway. But if we choose the pivot right here, where this cable attaches, then we can ignore this, this tension force when we're doing our torque analysis. So the next thing is just to add up and sum up all the torques and set them equal to 0. So this is the only positive direction torque. So I have T2 times 8 meters. All right, how did I get 8 meters? Well, I added up the distance from our pivot right here. That's 1 meter plus another 5 meters is 6 meters plus 2 meters here is 8 meters. So 8 times T2 minus 1 times 980, that's this torque here, minus 4 times 490, that's this torque here, minus 6 times 686 is this torque here. And these distances, 1, 4, and 6, are all found very easily just from these measurements that were given to us in the problem. So doing the algebra here, we can add up all these numbers here and solve for T2. I'll skip going through the algebra steps. It's nothing very exciting, but we end up with T2 is equal to 882 newtons. So that's our tension in this cable over here. Now we can turn to this cable here. To figure out this cable, the easiest way to do this again is, since we know all these other forces now, let's just make sure all the forces balance in the y direction. So the sum of the forces in the y direction is 0. So I've got T1 going up, T2 going up, and then these three forces are all pointing down, so they're going to all be subtracted from T1 and T2. Remember, T2, we just figured out here is equal to 882. So once we plug in 882 here for T2, we can just on our calculator add all these numbers together and bring it to the other side to solve for T1, and we end up with T1 is 1,274 newtons. So again, in these problems, you can see our strategy is we're doing two things. We're summing up the torques and setting them equal to 0, and then we're summing up the forces and setting them equal to 0. So this example is considerably more difficult because it involves an object at an angle. The nice thing about the scaffolding problems and the boards on the scales and those problems that we've done up till now is everything was horizontal and vertical. All the forces and the object was horizontal. In this problem, the object is this ladder, and it's leaning up against a wall at a 60-degree angle. So obviously what we're going to have to do here is work with vector forces and components. So we're going to have to do some basic trigonometry to figure out the components of the various forces and the torques and so forth. So this is a problem out of your textbook. It's example 8.4, at least in one of the older editions of the textbook. A ladder leans against a frictionless wall at an angle of 60 degrees. So we're going to assume this is something very slippery, like maybe it's like a glass window or something like that. Here's our angle down here. What is the minimum value of mu sub s, the coefficient of static friction with the ground that will prevent the ladder from slipping? So the complete solution of this problem is shown in your textbook. Again, this is example 8.4. So you can look at that if you want more details. I'm going to just kind of go through sort of briefly here the outline of this problem. So you can see the diagram here. This is the ladder leaning up against the wall, and the various forces are all shown here. The ladder has a mass and weight, so that's this weight force right here. Remember that it acts at the CG of the ladder, which is halfway up the ladder. There are two normal forces involved in this problem. The floor is pushing up on the ladder. Here, this one's called N1. And then the wall is pushing out on the ladder. That is the normal force, N2. And remember, there's no friction force along the wall here, so there's no vertical force here. But there is a friction force down here that keeps the ladder from slipping. And the ladder wants to slip out away from the wall like this, so the friction force is pointing in the opposite direction to keep the ladder from slipping. So that's the F sub S shown here. So the first step is we can find out what N1, this normal force here, is. You notice in this picture, the only two vertical forces are the weight down and normal force 1 pointing up. So since this is an equilibrium, those two forces have to add to 0. In other words, normal force 1 is just equal to the mass of the ladder times g, the weight of this is just the weight of the ladder here. All right, in step 2, we're going to basically add up all the torques and set them to 0. Again, this is our requirement for static equilibrium. So if we look at this picture here, we've got, they pick the pivot down here at this point here. Now the reason for doing that is there are two forces there, and neither of those are going to generate any torque if we choose our pivot right here. So again, the choice of pivot is arbitrary. You can pick a pivot anywhere, but this will simplify the problem. This is a tough problem, but it makes it a little bit easier by choosing this point as a pivot. So if we do that, what are the torques? Well, there are only two forces that are not at the pivot. So N2 is up here and weight is right here. Now the weight force pointing down, that's trying to rotate this thing in a positive counterclockwise direction. So we have to figure out the perpendicular component of weight, which actually would point along in this direction. Your book uses the moment arm technique to find this torque. So in other words, you take the weight and you extend it down here till you get to the floor, and you measure this distance here, D1, which is called the moment arm. Okay. The other torque is this one up here, and again, this force points straight out, so they calculate the moment arm, D2, as basically the height of this force here down to the floor. Okay, so that's D2. So D2 times N2 is the torque there. And this one, remember, this is rotating the ladder in the clockwise direction, which is negative. So that's why we have the minus sign here. So we can solve this for N2, and we get D1 times the weight divided by D2. Now we can do we can do a little bit of trig here to figure out what these distances are. D1, all right, is this distance here. Notice it goes from the bottom of the foot of the ladder to the halfway point, extended downward, all right? So this is going to be half the length of the ladder, which is this hypotenuse right here. This is L over 2, and then we multiply that by the cosine of 60 degrees to get this side of the right triangle down here. Okay, so that's D1. D2 is given by, remember, we can use this right triangle up here, and the hypotenuse is L, all right, the length of the ladder, and this time D2 is this portion here, which is the sine of 60, okay? So, and then let's see, what's left? Well, this is W, this is the weight of the ladder, which is mg. So putting in all the numbers here, notice the L's cancel. Here, this L cancels that L. And we end up with 0.29 times mg. So that's this normal force here. So the last step now is to add up the forces in the x direction. So in the x direction, or horizontal direction, we have N2, positive direction, minus this static friction force pointing to the left, and that those together have to add to 0. So static friction, the maximum static friction force, remember, is mu sub s times the normal force. In this case, we're talking about the normal force 1, and remember that was solved here for mg. So solving this for mu, all right, we can move N2 to the other side. Mu is equal to N2 over N1. It's just the ratio of the two normal forces. And N2 we found was 0.29 mg, N1 was mg, so the mg's cancel. So notice we don't even have to know the mass or the length of the ladder to solve this problem. The L's canceled here, the M's canceled here, and all we're left with is our answer. The static friction coefficient must be 0.29 or greater. Let's now turn to a somewhat related topic, but a little bit of a change of pace for us. And this has to do with stability and balance. So it's kind of interesting to think about how we balance when we're standing or sitting or walking. For our body to remain stable and balanced, the key thing is to have our CG, our center of gravity, directly over the base of support. Now, what that means is if we're standing on our feet, then obviously our support base is our feet, okay? So as long as our CG, wherever that is in our body, as long as that CG point is directly over our support base, in other words, somewhere over the length of our foot, we will be in balance, okay? So in this picture here, the CG being here, notice if you extend that downward, it is not over the guy's feet. Okay, so what's going to happen here is he's going to fall forward. There's going to be a net torque on him that's going to cause him to rotate. In this picture here, though, notice the CG has been shifted back by the position of his legs. So now the CG is over his feet and he will be balanced. This picture of the dancer here doing this pose here looks, like it could be very awkward and unbalanced, but the fact that she is apparently holding this pose here means that her CG, we know it must be right in here somewhere because her support base is just the tip of her toe here. And we know to be balanced, her CG must be directly above that support base. In this picture here, with this guy standing in this kind of leaning position, well, this would not be possible because if his CG was somewhere around here in his midsection, notice if we trace that straight downward, it's not above where his feet are touching the ground, so that means he's going to fall over in this direction. Here's a fun challenge that I would like you to try at home, and you can also challenge your friends to it. If we were in class together, I would pull out a nice crisp new $20 bill and offer anyone in the class the $20 if they can just do this very simple task. All you have to do is stand facing a wall with your toes against the wall. So notice you just scoot right up to the wall, press your whole body against the wall, all right? And then all you have to do is stand up on your toes, like the guy is doing here, and just hold that position for a count of 5 seconds. It sounds pretty easy, right? You can, try doing it without the wall. It's very simple. Now try doing it with the wall and see if you can do it. So I'd like you to pause the video now and go find a wall somewhere in your house or apartment or wherever you're at right now, and give this challenge a try. Also, make sure that your feet are right up against the wall. You have to make sure there's not like a thick baseboard or something down there. You need your feet right on the wall. But give it a try, and if you can legit do this, and maybe have someone video it, send me the video and I will gladly send you $20. All right, I hope you had a chance to try that. The question is, why can't you do it? Well, remember that your center of gravity, let's say, is right here, in the center of your body. And so when you're standing like this, balanced, your CG is, of course, over your support base, which is your feet. The problem is when you go up on your toes, your support base has moved forward. Your flat part of your foot and your heels are no longer touching the floor. So what happens is, in order to stand on your toes, you have to lean forward a little bit. You have to lean your CG forward. And if you do this without the wall in front of you, of course, it's very easy, and you don't even probably know you're doing it. You're subconsciously just inching your body forward just a slight bit to get your CG over your toes. But of course, if the wall is in front of you, that prevents you from leaning forward, and as a result, you will fall backwards every time. So again, if you haven't tried the challenge, again, please do it, and keep in mind, do it with and without the wall in front of you, and see if you can detect that shift forward in your center of gravity when you go up on your toes. Here's another fun challenge, and again, I highly encourage you to do this at home to get a little hands-on physics here. So this one is another good one. This time, stand up straight with your heels and back against a flat wall again, and all you have to do is bend over and touch your toes and just hold it for 5 seconds. So again, it sounds like a simple task, right? Without the wall there, it's very easy to do. Try it first without the wall, and then go and do it with the wall. And again, this is one where if you can do it for 5 seconds, I'll send you $20. Um, but maybe you can also challenge or bet one of your friends some money on a couple of these. They're awfully fun to do. So related to what we just talked about, we were dealing with stability of the human body, which is pretty cool and kind of fun to play around with. But there are other practical applications of stability and balance as well. For example, safety in an automobile is critical, and the stability of a car relies again on the fact that the CG, you want to have it over your wheelbase here, the place between your two wheels here. So if we have a car that goes around a turn too fast, it may start to tip. However, if the CG is over here to the left of the pivot here, the pivot now is this one wheel that's remaining on the road, then the car will safely rotate back down and land on all four wheels. But we get to a critical angle here where if we go past that critical angle, now the CG is to the right of the pivot, meaning the car is going to rotate to the right and the car will turn over, okay, which is a serious problem, obviously. So there is, we won't go through the mathematics here. If you're interested in it, you can look at these slides or in your book. But there's a critical angle that has to do with the track width. In other words, how wide apart the tires are and the height of the CG. And so the key thing here, well, let me go to the next slide. The critical angle depends on two things, the width of the tires, all right, how far apart they are, and also the height of the CG. So we want a wide wheelbase track width here, and we want a shallow or a low CG for balance. So if you take something like a Ferrari, a sports car, a high performance vehicle, it's going to have a large track width and a relatively small CG, and that gives it a very large critical angle, meaning that anything less than this angle and you'll be safe. If we look at a typical passenger car like a Nissan Sentra, it has a slightly narrower track width and it has a slightly higher CG, giving it a lower critical angle here. And then in the extreme, this is an older model Ford Explorer. One of the problems they had, this was a few years ago now, but SUVs were turning over and people were getting seriously injured. And the reason for that is the track width was not wide enough for the height of the CG. Notice how high up the CG here is. And this high CG makes this vehicle less stable when going around turns. Notice it has a much lower critical angle. Okay, that is it for this part of our lecture. I will see you in part 2.